Okay, welcome. This is the week 9 webinar for the online statistics class. And today we're doing something that we haven't really looked at much at all in this class. And this is the big chapter where we get to do it. So let me talk about the plan today. The idea is, as always, I'll answer any questions you have. So please, stop and let me know if there's any questions. You could put them in the chat box if you want, or just say them. And then we're going to use something called the chi-squared distribution. We've had other distributions already. We've had the normal distribution, the uniform distribution, the binomial distribution, the student's t-distribution. We've had a lot of different distributions, but this week is all about the chi-squared distribution. And it's going to be used to do some different tests, hypothesis tests. And the first one we'll look at is the chi-squared goodness of fit test. And that's going to be looking and seeing if one distribution fits another known distribution. So a distribution of something that you don't know, does that fit something that you do know? Then we'll look at chi-squared test for independence. And that will be about saying, well, we got these two things. If you know one, does that help you learn about the other? And we talked about independence a long time ago in chapter 3, when we talked about whether the two things were independent or not. This is actually kind of a step up from that. Instead of just, is this independent from this, as these are two things that could happen, it's these whole categorizations independent with this other whole categorization. And that's what we'll look at. And then finally, we'll get into the chi-squared test for homogeneity. And that is another hypothesis test. And that's going to be seeing whether this group and this group have the same distributions when you don't know about either group. You just have samples. And it turns out this whole chi-squared, hopefully you all know that square, you put a little 2 on top of a number and that makes it squared, like 3 with a 2 on top is 3 squared. Chi is a Greek letter. And you may think it's X because it kind of looks like an X, but it's kind of a curly X, and that makes it a chi, which is a Greek letter. And then there's a square. I am not going to get into all the deep math, but in the mathematics behind everything we're going to be doing, there's a square involved that you'll never see. It's just going to be hidden in the calculator. And you can trust me that it happens. And the main thing to know about the chi-squared distribution is if you square a number, any real regular old number, you can never get a negative number. So the idea is when we have any of these chi-squared tests, we only get positive possible values, which means that you only get a right-tailed test. There is no left-tailed test. There's not a two-tailed test. So it's never a not equal to or a less than. It's always a greater than for this chi-squared. And that's because it's always positive. So that is the plan for today. Let me stop. Are there any questions about anything? This is week 9. It's an odd week, so there's no exam this week. Next week you'll have one, but not this week. So this is a week I do want to let you know that you should definitely be thinking about your projects. If you're not sure about partners, make sure you have partners. But then because there's a good chance that you'll be working with the same partner. You don't have to, that you worked with in the project 1. But please post your project idea and any questions you have on the project 2 discussion board. And I look at that pretty often. And then any questions you have, I'll answer. Or if you post your idea, I'll let you know if it'll work. And sometimes I'll say, well, it'll mostly work, but you got to change this little thing. Kind of like same idea of project 1. But this is a time, again, it's a light week when it comes to there's no exam. And this particular set of stuff isn't necessarily harder than normal, but you should be really thinking about your project. You should all be ready to be doing it. Are there any questions? Are there any questions? Okay, if there's no questions, I think I'm going to talk a little about distributions. So first thing, what was the shape of the uniform distribution? In a word. Wasn't Bell. That was going to be the next one I'm going to ask. The uniform distribution. What's the shape of the uniform distribution? It's a word that even children know. Remember? Up? Not quite. Starts with an R. Remember? I know it's been a while. That might be why you're forgetting. It was a rectangle. Do you remember that? The uniform distribution, you draw a rectangle, and then you say, if you have a uniform distribution, you look at the area of the piece of the rectangle. You remember doing that? Yeah, it's been a while, but it's important. And then the shape of the normal distribution, that was the bell that you said recently. A normal distribution is bell-shaped. The chi-squared distribution is going to have a different shape. And it turns out there's something called degrees of freedom. So let me go and I think the best is to do it this way. If you're ever wondering how do you get to these things, if you go to this interactive statistics button, and I scroll pretty far, then there's a visualize the chi-squared distribution link. And I coded all this stuff. And this is the shape of the chi-squared distribution. You'll notice, hopefully, that we have 0, 2, 4, 6, 8, 10, etc. There's no negative numbers because a square can't be negative. A square of a regular number cannot be negative. So the first thing is it goes up and then it goes down, and you'll notice the shape is somewhat skewed right. It's unimodal because it has one lump, and it's somewhat skewed right. And we're going to be looking at hypothesis tests where you're going to have a test statistic. Let's say it was 8. That would be like right here at 8. And then to the right of that, that's the shaded in region. The p-value is the area to the right, and it'll always be to the right. Okay, it turns out there's something called degrees of freedom, which has something to do with kind of how many possibilities there are. And if the degrees of freedom is higher, for instead of 5, let's say it's 14, then you'll notice that it's still slightly skewed right, but it's looking more and more normal, it turns out. On the other hand, if the degrees of freedom is 1, it's just perfectly skewed right. It has a super high area. If it's 2, then it's a little less skewed right, but still very skewed right. If it's 3, now you can kind of start seeing that little bellish thing, and it changes as we go. That's the chi-square distribution. The mathematics behind it is way too hard for this class. You are not responsible for it, but hopefully you can trust me that when I made the calculator, it all works. Sound good? But I do want you to just get a little feel for what it looks like a little bit. Any questions on the chi-square distribution? Okay. So one thing, again, is that there'll never be a left tail because it's just gets stopped at 0. So we're only going to be having right-tailed tests, it turns out. It's not a greater than. We'll see what we're talking about. It's that the kind of the chi-squared value is greater than something. It's kind of the idea. Okay, so that's the idea of that. Now I want to ask you something. we have spent a lot of time in the last month or so. We've been dealing with quantitative data, whether it's confidence interval or hypothesis test. We've also been dealing with the yes-no survey question, confidence intervals and hypothesis tests, right? We've been doing that for a while now. What else is there? What other kind of survey questions could there be besides the yes, no, and quantitative where the answer is a number? Yeah, categorical. Examples of that might be, what is your race? You're not going to say 73. You're not going to say yes, right? You might say Hispanic, right? You might say African American. You might say white. You might say Asian. That it's a word in terms of what your race is. There are many, many, many survey questions where you have a categorical variable. Others might be, what breed of dog is that? You're not going to say a number. You're not going to say yes or no. You're going to say it's a, Lhasa Apso. That's what I used to have. If you don't know that breed, that's okay. There's a golden retriever. Okay. A lot of times you're going to have a survey question where the answer is not yes, no, and it's not a number, and we haven't touched that yet. Now it's time to touch it. Does that make sense? So it is important. It does come up in lots and lots of different examples, applications. So let me give you an example. Okay, so here's an example. And it is in California, 39% of residents are Latino. 35% are white. 16% are Asian or Pacific Islander. 10% are other races. So you can think about the survey question here is, what is your race? And as I had just mentioned, there's not a quantitative, there's not a number answer, it's not yes or no, it's a word, okay? There's different races that you could be, but they are all words or not numbers, okay? No one puts numbers to races. That's why I like this example, because we can't do it using anything we've already done, okay? Hypothesis test for the difference between means does not work because these are not means, or okay? So then the question is the distribution of races different for California community college students? That's actually a very important question that the community colleges care about. One thing is we want to make sure that we serve students from California, okay? And you don't have to be in California to take our classes, but most of them are. Probably not in this class, but most are in California. And we want to make sure that we don't have any discriminatory actions or anything like that. We'd like to be kind of like where we are. So let's suppose that a survey was done of 300 California community college students. 125 were Latino, 92 were white, 33 were Asian or Pacific Islander, and 50 were other races. Okay, what can be concluded at the 5% level of significance? Okay, any questions on the question first? Any questions? So as I mentioned, this is very different than testing between two means or a proportion, because here we have a lot of different choices. It's not the proportion of one thing. We got the Latinos, the whites, the Asian Pacific Islanders, and the other races. Okay, there's 4 different choices here, and they're all word answers. So what we want to look at is the racial makeup the same, or is it different at California community colleges compared to the racial makeup of just California residents? Any questions on the idea? Okay, I do want to let you know, I always give a heads up. These numbers, I totally made these numbers up. A survey was done. There was probably a survey someday, but I made these numbers up. These numbers here, the 39%, 35%, 10%, and 16% and 10%, those I looked online. And the good news nowadays, compared to when I first taught this class, it's so easy to find stuff. Looked online, I was able to quickly find the percentage of the different races in California. All right, so here's the thing, and this is very different from any hypothesis test we've done so far. All the other ones, when we looked at H naught and H1, I told you you had to use symbols. Do you remember that? So you would have to write that mu symbol, and then you would write equals 12 or something. Okay, or maybe you'd write P1 equals P2. Okay, when we're talking about this kind of study, symbols don't really work. So instead, for this chapter, we're going to use sentences for H naught and H1. So let me read the H naught for this example, and that is the distribution of races at California community colleges is the same as the distribution of races in California. Okay, I highlight or colored the word distribution. Why am I highlighting and screaming the word distribution right now? We've done this before. What does that mean to y'all? Remember? We've had this kind of thing before where I highlighted it and I yelled it loudly. So if I yell the word distribution, what does it mean? What does it tell you? Let's see y'all jumping in. All right, if you don't want to tell, I'll tell you. If you don't have that word in the hypothesis in H naught, and it turns out H1 also, then I take out points. Okay, so you don't want to lose points, do you? Because this is all about distributions in this particular hypothesis test. Okay, H1, once you have H naught, especially as an online class, so it means you're typing everything, then all you have to do is copy and paste H1, and then just before the word the, you put the word not. So H1 is the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions on that? Okay. The test that we're going to be using, the name of the test. So for this chapter, and actually for all the rest of the chapters, for every test, we're going to have a name for that type of test. The name for the type of test is the goodness of fit test. Often you'll call it the chi-squared goodness of fit test because we're going to be using chi-squared as our test statistic. But it's the goodness of fit test. And the reason why those words are used is what we're doing is we're saying, is there a goodness of fit for the distribution of California community colleges? Does it fit in a good way? Is it the same distribution as races in California? And that's why they call it a goodness of fit test. Is it a good fit? Is California community college distribution a good fit for the distribution of California races? Any questions on this idea? Okay, just like most of the things we do in this class, there's a step-by-step process. The first step, I guess I should say, because I haven't said this before, but it's obvious, read the question. And then the second step is to write down the null hypothesis. And when we're talking about chapter 11, talking about this week, it's going to be in words always. And then the next step is to write down the alternative hypothesis, and that will also be in words. And there's really a template. The distribution is of whatever you're talking about that you don't know about is the same as the distribution of what you do know about. Whereas H1 is a distribution of what you don't know about is not the same as a distribution of what you do know about. Any questions on that? Okay, the next step you're going to have to do is I'm going to ask you, what is the name of the test you're using? And in this case, it's called a goodness of fit test. A goodness of fit is used whenever there's a known distribution and you take a sample and you want to see if the population that you don't know is the same, has the same distribution as the known distribution based on the sample that you have. Any questions on that idea? Okay, so then the next step is to create a table. And this is an observed and expected table. So here's how the table works. Sometimes you'll see it with rows and columns this way. Sometimes you'll see it backwards. It really depends on what fits on the page. So the calculator, actually, if I remember right, it goes the other direction. But the idea is there's an observed row and an expected row. I usually use O and E. O for observed, E for expected. And that's standard, by the way. And then for the columns, in this case, it is all the different possible answers to the survey question. The answers were Latino, white, Asian Pacific Islander, and other. Those were the answers that you could have. Any questions so far on the table? Okay, so then once you have kind of written the idea of the table, now we need to fill in the table. So I'm going to start with the observed Latinos. What is the observed Latinos? And that's the observed from the sample that was collected. How many Latinos were there? Yeah, there are, it says right here, 125 were Latino. So the observed for Latinos is 125. Is that clear? Okay, good, good. Okay, how many observed whites were there? Yeah, now it's going to be 92 because it says 92 were white. How many observed Asian Pacific Islanders? Yeah, 33. And how many observed others? That's 50. Any questions on that? Okay, now we're ready for the expected. The expected is what you would expect to have if it perfectly fit the distribution of the known population. The known population in this case is California. Okay, so we have a sample size of 300 community college students. How do we find out how many of those we would expect to be Latino if they have the same distribution as in California? How do we find that out mathematically? The hint is there's a little bit of math, nothing too hard, but a little bit of math. What do we have to do? Any thoughts? Here's a hint. 39% of residents are Latino. And we are surveying 300 people. Not quite division, One more guess that it's kind of the opposite of that. Yeah, we multiply because we take 39% of 300. And to find 39% of 300, you multiply. You have to turn the percent into a decimal. And let's write this out, 0.39 times 300. Any questions on that? Any questions? Okay, so 0.39 times 300, that equals to 117, if I did it right in my head. I don't recommend doing it in your head, though. Let's see if you can guys check my work. So you get to? Yeah, sometimes they call me a human calculator, but you're not responsible for doing it in your head. You should use a calculator, okay? And it's basic calculator. You don't even need the fancy stats calculator. We'll get there in a bit. So the expected number of Latinos were 117. Is that clear? Okay, 35% are white. So if we want to find the expected number of whites, we do the same idea, except instead of 0.39, you go 0.35 times 300. Any questions on that? And that is 105, if I did it right in my head. And that's the expected for whites. Okay, next, we are told that 16% are Asian or Pacific Islanders. So then we're going to take 0.16 times 300. And that's 48. So our expected for Asian Pacific Islanders is 48. And then the others is 10% or others. 0.10 times 300. That one you might be able to do in your head, but that's an easy one. What's 10% of 300? Yeah, 30. Any questions on that? Okay. So once we have that, let me double check. 117, 222, 207. Yep, it works. Okay, I just wanted to check it. They add up to 300. All right. Now that we have our data and our observed and our expected, any guess on what the next step is? And we've seen this for hypothesis testing before. What's the next step is the question. What is the next step? When I tell you, you'll say, of course. Should I tell you? No, there's no mean, actually. There's no mean on this. This is all qualitative data. There is no mean. What we're going to do is we're going to find the test statistic and the p-value using the calculator. So now I'm going to go to the calculator and see if you can tell me what calculator number we're going to use. Yeah, it's number 21, goodness of fit. When I made this calculator, I tried to make it really obvious, so there's no tricks or anything. Okay, so with this one, it says, what are the observed values separated by commas? So now what I need to do is, let me just copy and paste. And put in commas. And then it says, what are the expected values separated by commas? So for that one, I'm going to copy and paste the expected row. and separate them by commas. Any questions so far? Okay, then I hit calculate. And take a look. Okay, this again is read chi-squared. Okay, and it's spelled C-H-I, but it's still pronounced chi. Okay, and chi-squared is around, how about 20.2? The p-value is 0.000, maybe 1/6. So the chi-squared is 20.2. And the p-value is 0.00016. I think I'll make that a little bigger so you can see it better. Any questions at all on finding chi-squared and finding the p-value? All right, so now it's time to write our conclusion. We have a p-value. What do you think we can do by looking at that p-value? Now that we've seen lots of hypothesis testing already. This is our third week of hypothesis testing. What can we do? Shows a chance of the distribution not being the same. It's a little more complicated than that. It's the question is not how do you interpret the p-value, but how do you state your conclusion after looking at the p-value? Remember? I'll put the first word down. There. That might help. Does that help? I always like to start out with that word on the conclusion. Remember the next few words? No, not a chance. All right, let me write it out. There is strong, statistically significant evidence. Do you remember those words? This is our third week of using them. And strong because the p-value is less than 1%. That's kind of our definition of strong. To conclude that. And now the cool thing, it's a great thing about online versus having to write it on a board or something, is all I have to do is copy and paste H1. There'll be one little tiny more thing, but nothing big. And I need to take the and turn it in lowercase. So there is strong statistically significant evidence to conclude that the distribution of races at California community colleges is not the same as the distribution of races in California. Any questions on applying a goodness of fit test? You think I've ever used a goodness of fit test for something that I did, outside of the college? And the answer is yes. So yes, a few times, several times in consulting work I did for statistics. The other one that I like to say, which was really fun, is that I think I've mentioned that I used to be a heavy card counter in Vegas at the casinos. And what they would do is they would bring in cheaters. That's what the casinos would do. They were run by the mafia. And what I would do is I would have to decide whether they were cheating or not. Okay. And what I would do is I would do a goodness of fit test and watch the cards that they're dealing themselves as the dealer is dealing and see if what they're giving themselves fits the distribution of cards. Okay. By the way, this was really hard because I had to do it all in my head. Okay, while playing. But it worked. And I was able to tell if they were cheating. And then if they were cheating, what do you do if they're cheating in those days? Oh no, you don't kick them out. They're mafia. The last thing you want to do is yell at the mafia. You just walk out of the casino. Yeah, they kill you if you do anything like that. So you just walk out of the casino. They don't kill you on that one. So I would leave the casino and then I would come back and then hope it was a different dealer. That's what I would do. So it worked. I never lost when I played when I counted cards, but I used goodness fit test for that. It was kind of a fun one. I figured I'd give you an example of what I used in my daily life at one time. Now, but by the way, it's a whole different thing. Don't think you can win in the casinos, by the way. Okay, especially not blackjack is what I played. Okay, ready for another example? Unless there's any questions about this one first. Okay, so this one's gonna be different. Does it matter what season a person was born when it comes to the type of car they drive? You ever thought about something like that? Okay. I don't know when you were born. I was born in the summer, by the way. Okay. And the table below says the season and car type. So the seasons are spring, summer, winter, and fall. Hopefully you all know those are the seasons. And the car type are sedan, SUV, and other is what I've decided to call different cars. All right. So just a note, just to make sure you know how to read this table, what does this 62 mean? Yeah, it meant that 62 of the people that were surveyed were born in the summer and drive an SUV. Do you see how that works? So it's important to understand what these numbers mean. These are the counts of those who had both that row and column. Okay, so 50 would be born in the fall and drive something other than an SUV or sedan. Any questions on that? Okay, so it's important that you understand how to read this table. How is this different than the last example? And the hint is it's very different. And not just, seasons and car type, but how is it different in the kind of question this is? Okay, it has proportions. Actually, the others did too. If you look at these, 39%, that was a proportion, right? But it has something very different. Okay, let me tell you what this is. If you notice, what would the survey be? What are you going to ask the person? It's not a yes, no question. Actually, there's no yes, no question on this one. Okay, if you don't know, let me tell you, you're going to ask two questions. The first question will be, what season were you born in? Spring, summer, winter, or fall? And the second question will be, what kind of car do you drive? Sedan, SUV, or other? Is that clear? Both of those questions are qualitative, and they're not yes, no. Does that make sense? And what we might be interested in is people who were born in the winter. Do you think they're more likely to drive a sedan, for example? Right? Maybe drive an SUV, or maybe they're more likely to drive other, or maybe it doesn't matter. Knowing that they're born in the winter doesn't tell you anything. You see that? Any questions on that? So this is a very different test that we're going to use. It turns out the math has that chi-squared distribution still, as will everything we do today. But we're going to be looking at what's called a chi-squared test for independence. Okay, so that's going to be the name of the test we're going to be using. And that's used when we have two survey questions that are both qualitative, and we want to see if they're independent or dependent. Any questions on that? Okay, so now it's time to state H naught. H naught is going to be the following, and that is the season a person was born in and the person's car type are independent. And I am going to shout the word independent. So the season a person was born in and the person's car type are independent. What does that mean that you're going to have to make sure of? Yeah, you better write it or you lose points. What is the opposite of independent? What word is the opposite of independent? Yeah, dependent. So the H1, I'll do exactly the same and erase IN. The season a person was born in and the person's car type are dependent. Any questions on that? Okay. And then we need to go ahead and use a calculator. The goodness of fit calculator is not going to work, by the way. So I'm going to go back to the calculator menu. And hopefully you can tell me what calculator to use. Should be obvious. Yeah, number 22, test for independence. Okay. And what we have are first, second, third, fourth, fifth, sixth, seventh, etc. And A, B, C, D, E. Okay, I want to let you know mathematically, whether you take this or you like take what's called the transpose, which means you just switch the rows and columns, that actually doesn't change anything. So you do whatever's easy to type. Okay, so if turns out if there are 8 columns, you make the column the rows instead of that, instead of the columns. Okay, but for this example, we'll be able to do it as it says, 73, 81, 76. So 73, 81, 76, and D will be 78. Leave E blank because it doesn't have values. The second one will be 65, 68. $62, $64. And then the third row will be 43, 51. $48.50. Any questions on entering the data into the calculator? Okay, and then make sure you leave everything else completely blank. That's important, by the way. And then I hit calculate. And there we have it. Chi-squared is 0.48. And the p-value is about 0.998. All right, now again, we're at the point where you should know what to do next when you see a p-value of 0.998. What do we do? Yeah, exactly. It's not statistically significant. This is as big a p-value as it gets, basically, or almost. So that we could say there is statistically insignificant evidence to support the claim that, and then, as we've seen before, I can copy and paste H1. And I need to take that done, make it lowercase. And just to make it prettier, I'm gonna format it. So there is statistically insignificant evidence to support the claim that a season a person was born in and the person's car type are dependent. Any questions on that? By the way, I want to let you know, if you believe in astrology, not astronomy, astrology, then then you're going to not like the statistics people have done, because I try to be somewhat realistic. And they've done these kind of things where they've looked to see when you're born versus, your personality and all that kind of stuff. And they have like nothing to do with each other. It's always statistically insignificant. Kind of cool. Okay. If you look at kindergartners, sometimes it can be statistically significant, because if you're born, right when they start, right at the youngest time they can start, you're a younger kindergartner. But other than that, it doesn't mean anything hardly. Any questions? Any questions on the chi-square test for independence? Any questions? Okay, so this is done a lot, and it often is done when you have two survey questions and you want to find out if there's a relationship between them. Sometimes you'll hear the question will say, is there a relationship between the season a person was born in and the person's car type? And what we can do is say that they're dependent if you have a small p-value, or we don't have statistically insignificant evidence to support the claim that they're dependent. Will we ever be able to say they're independent? What do you think? Will that ever be the conclusion? That we can say they're independent? Yeah, the answer is no. The answer is no, because hopefully you know by now you never accept the null hypothesis. Okay? But you can say that it's statistically insignificant to say they're dependent, but you can't say they're independent by just data. Any questions on that? Okay, shall we continue on? Okay, so here's a different example. Do single men and women take the same type of vacation? Okay, very important, by the way, if let's say you're an advertiser, because if you're into advertising, or let's say you're in charge of advertising for some maybe airline company, then you want to decide if you have a group of men that's typically the audience, are you going to advertise differently than a group of women who are the audience? Do you see how that works? Okay, so this is an example that you would use, this for. The table below shows the results of the study. And we have male and female. And we have international, out of state, and kind of more local. Okay. And maybe when I say out of state, maybe I should really mean far away out of state, because if you're in Tahoe, out of state, I could walk out of state in about less than an hour walk. But that's not true for most people. Okay, so, and here's our table. So notice there were 29 of the surveyed individuals that were male and maybe tend to take international vacations. There were, let's say, 36 females who tend to take vacations that are more local. Any questions on reading the table? Okay, this is different than asking if the two things are independent. So this is one of those where the way the question is asked is important. It's not just the table. And here we want to say, are men and women the same when it comes to the vacation type that they take? Another way of saying the same thing is the distribution of vacation type the same for men as the distribution type of vacation type for women? So do you see we're comparing distributions? Any questions on this idea? Okay, so it kind of looks somewhat like a goodness of fit, because that was when you want to look to see if a distribution fit another distribution. But with the goodness of fit, there's a distribution, the entire population, and there's a sample. Here we have two samples. We don't know any population. Do you see that? It looks a little bit like a test for independence because it's a table with two qualitative survey questions. So this is kind of a mix between the two. And it turns out the math will be the same as the test for independence, which you'll never see because I don't do the math in this class, but you can trust me. But the wording tends to be closer to the goodness of fit test. And the name of the test we use for this kind of question is called a chi-squared test for homogeneity. Okay, when have you heard the word homogeneity or maybe homogeneous? Or homogenized? Okay, yeah, you might have seen it in biology. What does it mean in biology? Since you've seen it. Yeah, it's basically the same genetically. Do you see that? And that makes it homogeneous. Okay, so homogeneity is about the same. Okay, the genetically is a special example, but it's the same distribution of genes. In this case, it's the same distribution of travel type. Any questions on this idea? Okay, so, and by the way, you are going to be responsible for naming the test. And this so far, okay, and actually not even so far, all in chapter 11, we have 3 tests. One of them is a chi-square test for homogeneity. What are the other 2? See if you can remember the names, because they're important. This is our 3rd example, and it's our last one. Last different example. Yeah, test for independence. And what's the other one? Yeah, goodness of fit. Okay, so make sure you have those 3 tests understood and know when to use which, because it turns out that's typically the hardest part of this chapter, is to deciding which test to use. And for most people, that's a tough one. Okay, once we know we need to use a test for homogeneity, now we need to write down H naught and H1. And here's what we write. The distributions of travel type are the same for men and women. And let me take distributions, shout it out, because that's the big word. Got to have that. Any guess on what H1, how it's going to be different? It's not very different. How is H1 going to be different from H naught? So I just copy and paste. Yeah, exactly. You just before the word the, you put not. So the distributions of travel type are not the same for men and women. Any questions on that? Any questions? Okay, so that's a chi-squared test for homogeneity. So far, so good? What do you think the next step is? Yeah, we go to our calculator. Yeah, we go to our calculator. And this one won't work. I can go back to the calculator menu. This should be obvious. Which calculator do we use? Yeah, number 23, test for homogeneity. I even put it in the order at which I just gave the, presentation on. We only have 2 left, by the way, 24 and 25. Next week, we'll do 24. The week after, we do 25. Okay, that's all that's left. Here, it says, enter the observed values for each of the 2 samples, A and B. Hit calculate, and the chi-squared test statistic and p-value be calculated for you. Leave blank the last rows that don't have data values. So now we just type in the numbers. So we have 29, 47, 33. So 29, 47, 33. And then for B, 38, 42, 36. Any questions? That wasn't too hard, was it? Any questions? Okay, this can, in the real world, this can get kind of busy. So if instead of, travel type, what if it is, what state were you born in? Why would that be kind of messy? Would that be much harder? Hopefully you all know. Yeah, because there's 50 states in the United States, and you'd have 50 numbers for A and 50 numbers for B. I don't think I even put, because I won't test you on it, that many. You'd have to use a spreadsheet instead. And there is a chi-squared tab on the spreadsheet. If you ever, after this course is over, if you ever have to do a chi-squared test and you have more than, how many does this have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, more than 10 different categories, then you better use a spreadsheet then. The spreadsheet can go on and on and on. I hit calculate. And there we go. Our chi-squared is about 1.4. And our p-value turns out to be 0.496. How about? Just to note, I think it's worth it to go back and look at this. We actually have 2 degrees of freedom for this example. And if you look at the chi-squared value, which was 1.4, that's about here. And you look at the area under the curve to the right of that, that will be 0.496. So that's kind of what the picture of it is. You won't do too much of that, but it's kind of good to see that it's not that much different than what we did before when we looked at the normal distribution and we shaded in stuff and we found a probability. The P stands for that probability. Any questions? Okay, it's time for the conclusion. What's the conclusion? At least the first few words. Yeah. There is statistically insignificant evidence to conclude that, and now I just take H1, copy and paste. Hopefully you're seeing you can always do that. That's the good news. But take the and make it lowercase. The distributions of travel type are not the same for men and women. Any questions on that? Any questions? Okay, so again, these are all used pretty much, but they're especially used in like kind of higher level stuff, publications, and I don't mean higher math fields, but if you're going to be reading a published article, chi-squared is very common to be used. It's not the kind of thing you'll do in your day-to-day life, but you may read about it, or if you decide to get a master's degree, you may need to use chi-square distribution. All right, now let's do another one. A study was done asking people how far they plan on traveling for Thanksgiving. Okay, hopefully you know that Thanksgiving is in 9 days from the day I'm given this. Okay, the mean was found to be 120 miles. The standard deviation was 40 miles. The table shows the results. Is this distribution normal? Now, do you remember we have had times where we had to assume the distribution is normal? Do you remember having to do that sometimes? Okay, so this is one of the ways of actually deciding whether the distribution is normal. So we can actually do a test, say, yeah, it's normal, and now we don't need such a big sample size if we want to use a normal distribution. Do you see how that works? Okay, this is one of the tests. It turns out there's a more used test, and that's called the Kolmogorski test for normality. But again, that's more advanced than this. It's kind of an extra level of what we're doing. So we have less than 80, between 80 and 160, and greater than 160. And the observed were 56 of those surveyed traveled less than 80 miles. 61 traveled between 80 and 160 miles. And 12 traveled more than 160 miles, or will be traveling, I guess. Okay. By the way, what are you in? What do you think? How much are you traveling? Maybe you can pop in the chat box. Which one of these three? Are you less than 80, 80 to 160, or more than 160? Less than 160, that's not one of the choices. Could be between 80 and 160, and less than 80, those are both less than 160. Just let you know that. Okay, good. Less than 80, between 81. Oh, it's interesting. And I am, by the way, greater than 160. So I'm traveling to see some family. Okay. Now we want to find the expected. How do I find the expected? Let me start with this between 80 and 160. How do I find that expected value, that expected number? Any thoughts? And it's been a while since we've thought about this, but it's important. You don't jump in. There's something really nice about the number 80 and the number 160. If you take 120 and subtract 40, what do you get? What's 120 minus 40? It's not 140. Yeah, it's 80. And what's 120 plus 40? That's 160. So you can realize that being between 80 and 160 means that you're within one standard deviation of the mean. Any questions on what I just said? We subtracted the standard deviation, which was 40, from the mean, and we added it also. So see if you remember what percent of data will be within one standard deviation of the mean for a normal distribution. The hint is it comes from the empirical rule. I don't see y'all jumping in. That was 68%. Do you remember that? 68% is within one standard deviation of the mean when you have a normal distribution. That was the empirical rule. Now, it turns out if you take 56 plus 61 plus 12, you get 129. Okay? So the sample size is 129. If I want to see what my expected number of people are between 80 and 160, I take 0.68, the 68%, I multiply it by 129, and I get 88.72. Any questions on that? If I want to find out what percent are less than 80, then what I can do is I can say, well, if there's 68% in here, then 1 minus that percent, or 100% minus 68% will be out here on the outside. And then the left-hand side will be half of that. So what I do is I take 1/2 times 1 minus 0.68, and I multiply it by 129. So let me pause for a second. Any questions on how I came up with that math? So inside is 0.68. So outside is 1 minus 0.68. So the left-hand side is 1/2 of 1 minus 0.68. Then I multiply that by 129. And I got 20.64. And one of the nice things about the normal distribution is it's symmetric on the left and right. So if we expected 20.64 on the left, we expect 20.64 on the right. Any questions on how I came up with this calculation? Okay, what test should I use? Which of the three tests that we've talked about today should be used? Even if you guess, you got 1 in 3 chance, right? So what do you think? What test should be used here? Yeah, this is a goodness fit test because we know the distribution of the normal distribution, right? That's very mathematically known. What we don't know is the distribution of how far people are traveling for Thanksgiving. And we want to see, is that the same as the known, which is normal? So the test to use is goodness fit. Any questions on that? So then what I need to do is I go back to the calculator menu and I click on goodness fit. And I have my observed and my expected. I'm going to copy it, going to paste it, stick some commas in. And then I'm going to copy these guys, the expecteds. I'm going to paste the expecteds into the expected and put some commas in. Any questions on putting it in the calculator? And then I hit calculate. Okay, chi-squared is 72.9. What's wrong with saying the p-value is 1.11? I'll write that in, and I want you to tell me I'm wrong. What's wrong with saying that? There's something very wrong about that. In fact, this happened on the discussion post assignment that I graded today. Somebody wrote down that the p-value was, something like this. What's wrong with this? This can never happen. You can never have a p-value of 1.11. How come? I'll see y'all jumping in. Okay, P stands for probability. You can never have 111% chance of something happening. Yeah, P cannot be greater than 1. So this is not correct. So let's go back and look and see what we missed. What did we miss? What did we miss when I blindly wrote 1.11? 206, 20.64 is repeating. Actually, it's not, but that's not the issue. That's a different issue. It's really important. All right, if you don't see, let me highlight it. What's that tell you? That E negative 16. Yeah, it means we need to move the decimal place 16 places to the left. Okay. By the way, if you're using a smartphone, the smartphone is smaller, so you may only see the first little bit, and you got to scroll to find that E. But if you ever get a p-value bigger than 1, scroll or move your eyeballs and find that E. So it's E negative 16. The first time you move, you just move it. All the rest of them, you get a 0. So the first one is like a freebie, and the other 15, you get a 0. So the p-value really is not 1.11. It's 0 point, and then 15 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's very close to being 0. Any questions on that? So now the conclusion is there is strong because it's a very small. In fact, I'm going to write very strong because it's super small, this p-value. Statistically significant evidence to conclude that, and now I copy and paste H1. And make that the lowercase, that the distribution of Thanksgiving travel distances is not normal. Any questions? Any questions on this example? I just want to let you know that for good as a fit, there's really 3 types. I only have so much time, so I only gave you 2 of them. One type is when you have this known distribution that comes from like the Census Bureau. Okay. And that was when, if you remember at the very beginning, we knew what the distribution of races were in California. Okay. It's not some like special distribution like normal. It's just known percentages. That's one type. Another type is when you want to show a distribution is normal. And then the third type is when you want to show the distribution is uniform. Do you remember what uniform means? Especially when you have discrete data, like if there's only 4 different choices or something. Let's see, I'll jump it in. Uniform means the percents are all the same. So you take 100%, you divide by how many choices there are, and each choice has that percent. So if there were 4 choices, each choice would have 25%. If there were 10 choices, each choice would have 10%. If there were 5 choices, each would have 20%, because 100% divided by 5 is 20%. Any questions on that? So sometimes you'll want to be able to show a distribution is uniform, and that's the one I'm not going to do an example of, because I don't want to like tire you out too much. Any questions on any of these examples? Okay, then the next thing is the secret word. And the secret word for today, for this webinar, is qualitative. Do you remember what qualitative means? Yeah, it's categorical. So it means that the answers are a bunch of words and not numbers. And the chapter 11 and the chi-square distribution is really all about qualitative data. So that's why I use qualitative for the secret word. Okay, so I think I'm going to call it a webinar. I'm going to always happy to answer questions. I'm going to stop the recording, but thank you for joining. And then I'll stop my share also.